Thanks, Penway. Hello to everyone. Thanks everybody for joining us today. Much appreciated to give up of your time to join us and have a look at this. So to promptly move on, soil resistivity testing, and today's presentation is a practical presentation. It's not going to get particularly technical, although I'm happy to answer questions at the end. But let's have a practical look at what can happen on site that's going to cause errors and how we can minimise those or eliminate them if possible. So what are we going to learn today? Okay, there we go. Here's our takeaways. So what I'd like you to take away today is some knowledge on what measurements you can expect at any particular site. We'll do a quick refresh on the WENNER test, the most common soil res test. And how do we get some confidence in our measurements while we're on site? What are the causes of some errors? How do we remedy them? And how do we leave the site with what we came for, which was accurate results? And yeah, hopefully we've got some time for Q&A at the end. So just looking at the soil resistivity, I mean, it's a key factor for design input for earthing design. What can affect our soil resistivity? Well, it can depend on geographical components. So are we near the beach or the bay and we've got lots of sand in the soil? Are we up in the mountains? Are we on rock, which can be quite high resistivity? Are we on the alluvial plains? It's got a mixture of both, maybe underlying rock and a few metres of nice soil on top of the rocks. Moisture is another big input, so we try and measure when it's relatively dry. The higher the moisture content, the lower the soil resistivity will be, and there's charts you can look up on that. Temperature has an effect too, but not to the degree that the other two there. A few different methods. There's driven rod, Schlumberger and WENNER, the WENNER being the most common used method. And I'll have a look at that and we'll refresh it. A little on what to expect. Here's a table here with materials on the left there telling you whether it's clayey soil or silty or sandy soils, maybe gravel. Then moving further on into rock, even to bedrock. So you'll see that's generally arranged. So when we're in wet clay soils at the top there, we can have resistivities around 1 to 10. I've measured personally below 1, and you're right next to the salty sea table, the water table. And up in the mountains can be quite high. In fact, even an example we'll look at today, which was near the bay in Victoria, we had a couple of 100,000 ohm metres, about 4 metres below the surface. So that gives you a bit of an idea of what you might be looking for, what you might expect. Sorry, my presentation's not scrolling particularly well. Anyway, so the WENNER method, most common one, works on the 4-wire resistance measurement method, which, as we know, is push a current through separate wires to your voltage wires, so that when the meter does the calculation for resistance, we don't have the resistance of the actual test wires in the circuit. As you can see, we've got a current source at the top there. In fact, an ammeter or a current source is going to push current into one spike in the ground, across through the ground, past the voltmeter, back up the other current path, and go around that circuit while we're measuring the voltage across a specific set distance on the ground there. Of course, the meter's smart enough to know Ohm's law, R equals E over I, and come up with the resistance on the screen for us. Some meters actually are smart enough, if you input the distance between the states, A in this case, it'll give you the resistivity too. Resistivity formulas there, rho equals 2 pi AR, A being distance between the states and R the resistance. And as I say, just got to be careful with the meters that give you the resistivity, that you've told it what the distance between the stakes is. If you've moved the stakes and haven't told the meter it's any different, it'll give you a wrong result. So careful on that one. Okay, so what does a good set of results look like? So on the screen there, we can see there's a tabulated set of results on the left-hand side, giving us the distance between the spikes that we've set out through to the resistance we're measuring and even the apparent resistivity. When they're plotted, I've used seed eggs that many of you will know to plot these on the right-hand side there. You'll see that there's a nice smooth green line of best fit can go through those readings quite nicely. You might notice if you look closely, there's actually two sets of readings. The blue dots are the actual readings, measurements we've taken. And so this is a table of one set of results. We do a second set called an orthogonal. We'll look at that later. And that's what the second set of results is here. So they're relatively close. Seed eggs is giving us a, I'll just move something off the screen now. I can see it giving us a pretty small error between these readings. As you can see, the further we get out, the more likely your error is going to get a little bit larger. But this is a pretty good set of results. It's not confusing seed eggs at all there. So I'd be happy as a designer to accept those results and continue on and move into design. So a few things we want to do before we go to site. We need to plan, and when we get to site, we want to be engaged in the results. So before you go, maintain the equipment before going to site. Make sure that there's continuity on your reels, that there's no clips that are just about to break off from use, etc. Because Murphy has a way of jumping in your toolkit and going on these jobs with you, and he'll trip you up wherever he can. So maintain your equipment before you go. Make sure all the batteries are charged if you've got battery-operated equipment. Plan where to set the tests, which we'll go through today. So know where you're going and what site you're going to rather than working it out when you get there. Have a proper instrument set up and lead management. So, again, as you'll see, we're going to be swapping leads around. So it's nice to have them colour-coded so that when you're swapping them around, if they get a bit tangled up, that you're not going to get the wrong plug in the wrong hole to give you a wrong reading. Know what to expect and be inquisitive about the results too. Don't just blindly accept the result, write it on the pro forma and make it someone else's problem. As you'll follow through, there's ways to know that the result you're getting is accurate and you're confident with it, trustworthy. Take plenty of water with you. Salt water is even best. Just some salt from Coles or somewhere and put it in the water you take along to make salt water. And put plenty of it around your probes for good electrical connection to the soil. That's a winner every time, that one. I try to do it every time, even if it's moist, still put some salt water around your pegs for good contact. And repeatability and cross-check. So repeatability, if you've got to go back and check a result, check it. If it's unusual, check it again. And cross-check it with an orthogonal traverse as well. And plot your results as you go. So you can see what it's doing and if you've got some sort of unusual readings coming out. So if we have a look at this one here, we've got a set of results, Murphy's results. Murphy went out and got me a set of the results. You can see on the left-hand side there, and you can see how I've graphed them on the right-hand side. And the blue dots are the readings, and they're kind of a little bit up and down and all around the place. So I'm not really confident that these readings are true readings. In fact, if you have a look at the data on the left-hand side there, there's a rule of thumb I use in SOARES testing. If you double the distance between the stakes each time, your resistance you read should never go up. It can be the same, it'll never go up. So there's many methods. Some people use lots of different steps of the spacings here, but I like to just double them each time. And that way I can check the results, and they should go down each time. You can see this one's gone up again, and then it's gone down, down, down. So this immediately tells me that there's some problems with these readings here. It doesn't fall true for me. So Murphy's got amongst this one and given me some funny results. So let's see what we should be doing when we're planning to go out on site. So here's a situation, good old Google Earth. And we're looking to build a substation next to the rail here in this example. So can we do soil res testing here? Very difficult. We've got a lot of conductive infrastructure there, visible conductive infrastructure. Might be a little hard to see, but we've got a fence down the side here, a metal fence that's in contact with the ground. So if we're going to measure soil resistivity in here, the distance between the stakes, effectively grabbing a hemisphere of soil. So as the further you get out, the bigger the hemisphere of soil that you're measuring. And this steel structure here, the fence, and indeed the concrete with the reinforcing in it, if it's going to have influence on that hemisphere, it's going to interrupt your results. They're going to be lower than you think, than the actual soil is. So have a look at the site before you go and decide whether you can do it on the site or not. In this case, we couldn't, so we moved somewhere else. So site selection, before you get out of the office, the site selection is important. If we're going to do a substation on the corner here, plenty of green grass there with the subs going. We could go on the site there. We know there's no conductive infrastructure that's going to make our results have errors in them. If there was, we've got a nice park nearby, and don't be afraid also to go even a bit further away. You can go hundreds of metres away. And as long as the terrain is similar to where your job is going to be, you'll find it's a good representation of the soil res for the site you're going to be working on. That site I showed you next to the rail, we couldn't do soil res here. So we picked 3 sites around the circumnavigate effectively. Site down here, but as you can see, it's near the bay. There may be more sand in this area than our site. Put another site over here, further away from the beach, but it is still pretty close to a watercourse. So I picked a 3rd site as well, further away. And what we did when we looked at the 3 results, we found that there was a rock shelf about 4 metres underneath all of these sites, and it was 250, 300 k-ohm metres. So very, very high resistivity rock shelf. And then just looking at the top 2 layers of the soil, we could bring together quite a reasonable soil model so that we could use in the design of our substation here. So yeah, again, don't be too afraid to get further away and gain some more information about what might be happening there. When you pick an individual site, you're going to do a traverse. So you'll do a set of readings for your soil res in a line in a nice park, cricket park or a footy field, and we come up with a set of results. Now, parks are nice. However, you never know when potentially there's some irrigation pipes under there. We like to irrigate our parks, and if it's not done in PVC, if it's some older style irrigation pipes under there, you might actually be measuring the resistivity of the pipe, and your readings will be in error. So if we do a second traverse called an orthogonal, it'll be therefore won't have the same effects of a pipe going across the field in this direction. It won't have its results affected by underground pipework. So we can compare both of these, as we did in that first example, where you've seen that there wasn't a lot of error between the 2 readings. That's what we expect if there's no metal under the ground there. It's going to interrupt our readings. So how do we get around unseen conductive structures under the ground? We do an orthogonal traverse to ensure that we know there's no interference under the ground. So we're measuring in a place where we know is good to get some good results. So this is a typical meter, the Fluke 1625. And you can see here I've just drawn how it connects to our current probes and to our voltage probes or potential probes. It's pretty important to make sure our probe resistance is as low as possible. The meter can only push a current through a certain impedance. It's got its limits, as you'd imagine. So make sure on all of these stakes we give them plenty of salt water around them to get good contact with the ground. And tap them into the ground. We shouldn't put them in more than 5% of the spacing. Not so bad on the wider spacings, but on your 1 metre or ½ metre spacings, that means 2.5 centimetres or 5 centimetres. So make sure we tap these in as far as we can and get plenty of water around them to get good contact with the ground. So probe resistance is another problem on the job. Another way to ensure that we haven't got any errors is not only to do our first traverse and an orthogonal, but on each measurement that we take, and we'll have a look at a pro forma table next, but we can do what we call CPPC, which means you're putting a current on the outside spikes and you're measuring the voltage on the inside. We can swap them around, as I've noted here with the lines on those connections, to push current through our potential spikes and measure the voltage through our current spikes. And amazingly enough, you'll come up with the same reading. I can explain that in question time if you like. So we should get the same reading. So you push it one way and push it the other. If there's any DC stray currents or errors in the ground, when we average this will help cancel those errors. So here's a table you might fill out on the day. Here's your spacings down the left. You can put your CPPC measurement here, PCCP here, average them out, multiply them by this factor, which is just 2 pi times the spacing, and get your resistivity. So you look to make sure that your readings in both directions are relatively similar. If they're not, work on your probes, make sure they're tapped in, make sure they're well watered, make sure your connections on your clips are on there nice and solid, and they should be pretty close. As I say, do a plot on the day. As you move through from your 1 metre to your 2, 4, 8, etc. You should find that soil gives you a relatively smooth curve. If they're up and down and all over the place, something's going wrong. You need to go back and measure those, have a look at those measurements again. And yeah, go through those fault findings and like I have already. So if we do have a bit of a recalcitrant spike, if our meter's normally got warning lights on here, and they'll be flashing and telling you, I've got a problem on the E terminal, which is this one, or the S terminal, etc. I think this one's flashing at the time. It's off when the photograph was taken, so it's telling us that yes, here's got a problem. So you go out and you tap on that one and put some more water around it. But you can also, if these spikes are out 100 metres, from your most soil res kits, you can do a 3-point test or a forward potential test, they call it. There it is. I managed to get it up on screen. And you quite simply disconnect, in this case, if you want to measure the resistance of C2, effectively you're looking at it as a single source grid, point grid. Simply disconnect P2 at your terminal here and bridge those out. And this meter will put it into 3-point mode, and it'll give you a reading of the resistance at this stake. And you just change the connections so that you measure the resistance at each stake. You might find one that's relatively high, to go and work on that one, get it lower, remeasure it. Or indeed, even a balance. A lot of these meters like a balance from one side to the other to be similar in the impedances that they're seeing on each side from each terminal. This is a pretty handy method to know. You mightn't use it often, but when Murphy's around, that's a good one to cure the problem. So just in summary, I know it's a bit of a fly through, a lot to learn, but things to remember: site selection before you go out. Don't be afraid to go hundreds of metres away from where your site is if that's necessary. Proper test setup, so make sure you've got good lead deployment. So not only do you not trip over it, but as you're swapping from CPPC to PCCP, it can get a little confusing. Perhaps even colour code those leads, so that is less a problem. Cross-check the results, so do an orthogonal and also do your CPPC, etc. Plot it while you're on site, so you'll see if you've got a problem, and you can, while you're already mobilised, you've already spent your money getting there, go back and check those other readings and know how to test your probe resistance so that you can find that troublesome spike if it's 100 metres away without having to walk backwards and forwards to it. As much as it's good exercise, it does take time. So, and the last summary, make sure we're leaving the site with accurate results. If you've done all those above points, we should be doing that. So that is the end of the presentation. I'm just checking the time. Yeah, we've got some time for Q&A.